Hello all, welcome back. We are going to have a look at sine areas, in particular connecting this into definite integrals. I have a diagram here and you can see the part of the curve is above the x-axis and some of below the x-axis. If I were to look at the area or the shaded area, we simply need to add A1, A2, A3 and A4. It's just basically adding the areas. And if I were to look at the sine area means anything above the x-axis positive, anything below is negative. Therefore, the sine area of everything here is you add these two first on the top and then you take these areas away from it. So basically A1 minus A2 plus A3, but take A4 out of that. Now let's have a look at an example in terms of definite integral. The integral itself, if I go from a point, let's say A to B here, it will give you the area under the curve. Yeah, of course, what happens if I move the B to there is it will calculate the sine area. What it means is it will calculate everything above the x-axis as positive and below as negative, will deliver just the final figure. Let's say, for example, I have 5 square units there and 1 square unit here. In that case, if I consider the integral a to b fx dx, it will give me the 5 minus 1 value, which is basically 4. That's because the area above the x-axis is positive, which calculated as 5 when it does the calculation over here. And then below the x-axis, it will treat this bit as not just area 1, it's a negative 1 because it does consider the sine. So you got to be very, very mindful when you go through the points. When the graph is below the x-axis, it will give you negative figures, which means the final solution is accounted for everything. Hence, I get 5 minus 1, which is 4. But if I were to answer, let's say, the shaded area, that means 5 on the top, 1 on the bottom. I should have 6 square units as the answer, which means I need to definitely split. Let's say this is C. I need to split my integral from A to C first, which gives me value 5. And then also I need to consider C to B, which gives me value, well, because it's below the x-axis, it will give you negative 1. So to merge these two to get the answer, I only look at the absolute values, which means 5 and a 1, or rather more in integral form, I can write down the area as A to C fx dx and then C to B fx dx. And I know the second part delivers a negative value, hence I put a minus in the front to make it positive to get my area, shaded area. So I call it shaded area is in this formula. You need to make sure that you put the negative sign in the front of integral in case if it delivers a negative value for you. So let's go and do an example. Well, of course, what I just discussed are some properties. If I were to go from A to B, I can split the graph looking at, or the area, looking at A to C and then C to B, simply adding two areas together gives you the final area from A to B. And of course, if I consider a line, just one height here, a point, there is no area under the curve for that particular point. That means going from A to A itself. That's what it is. And in this case, what we are looking at is a multiple of fx. That means if I had the fx like that, and then the dilated form is like this, which is k times the fx. So this is kfx, and this was fx, the light blue color one. If I calculate the area down here and then multiply that with k, is exactly same as if I considered the area under the curve for kfx, which is the dilated version of fx. So that's the rule for that. And of course, if I have two curves, one is fx and the other one is gx, I can of course find the area between these two with a minus, and that gives me, if I were to consider in this case a to be here, I first consider the blue area and then I consider the orange area. If I took that off, I would end up with the area in the middle. So that's simply difference between areas. Now if I were to calculate fx plus gx, what it means is, for us, for that function, I had fx like that, and then of course gx here like this. Now if I were to consider fx plus gx, it is not the difference, it's the addition, which gives me the big function, which is like that, that is fx plus gx. And if I were to integrate that, what it means is the finding the area under that curve is basically adding the previous two areas. So this area underneath fx gonna get add on to the area here under the curve gx. That delivers me the full area for the both functions. And of course, if I swap the limits, in this case ab to ba, what it means is going forward I calculate positive areas, and then going backward I calculate negative areas. Therefore, to match them, they're exactly the same number. If it is here 5, this should deliver negative 5. How to make 5 to make negative 5 the same? Well, you got to put a negative in the front. So that's what I do. So simply putting a negative in the front if you swap the limits. And they're the rules or the properties that we use. Let's have a look at an example. Just to go through here, we need to find the area of the shaded region. So remember, shaded. Now you can see the graph is actually splitting at 3, or rather goes through the x-axis at 3. What it means is we need to split the graph or the integral. So the shaded area, first I go from 2 to 3, and then it's fx dx. In this case, fx is x squared minus 9 dx, and then you know this is below the x-axis, hence I get a negative value for that. Therefore, to make it positive, I need to make it minus in the front. So I need to put a minus sign in the front. Then I add a value. Basically what it means is this will deliver a negative something, right? Negative m. So to make it positive as an area, I need to put that minus in the front. That's what I did. And for the second one, I'm going to go from 3 to 5. And again the fx dx. Now I integrate. Of course, this is exactly the same function, but you must split where the graph goes through the x-axis. Now let me write the answer now. There's a negative sign in the front. When you integrate x squared minus 9, it gives you x cubed on 3 minus 9x, and the limits are 2 to 3. And then here again, x cubed on 3 minus 9x. Here the limits are 3 to 5. Now we are going to sub them in, leaving the negative in the front. 3 sub in gives you 3 cubed on 3 minus 9 times 3. And then, of course, the limit with 2, that gives you 2 cubed on 3 minus 9 times 2. We'll see whether we can simplify this one fairly fast. Then I substitute for the next part, which is with a 5 and a 3. I have written that here. Now we got the values. Now we need to simplify this one. If you did that, you would end up with 52 on 3. So we got the area. The main thing that you need to take away from this is the graph goes through the x-axis at a point, therefore you need to split the integral and put the sign negative in front of the area that you get under the x-axis. Otherwise, you would not find the shaded region. Rather, what you get is the sign area. For example, if I were to find the sign area, which means counting this negative and positive, I simply write 2 to 5 x squared minus 9 dx, and then I'll end up with the answer, which is 12, which is a little lower than 52 on 3. And you can clearly see the negative area has been taken into account. So that's it from me. You can try the next example as well. You need to expand the brackets before you do the integral here, and then split the graph, or rather the sections from 0 to 1, 1 to 3, and then write down the integrals accordingly. And then apply positive, negative in front of each areas to make sure that you count that negative values that are coming from these areas which are underneath the x-axis. Okay, ladies and gents, that's it from me. So the learning intention was to use the definite integral and apply that in sign areas. We worked on this example in both cases now. Hope you understand now what is the sign area. Okay, so let's stop here for now, and I'll catch you again in another video lesson. Bye for now.